architectural view. So this is actually good. This is good, right? Because it's Thanksgiving week, and we want a soft landing into 25-pound turkey dinner. Let's take a look. See, this is the block diagram. Is there anything you guys learned in this class? Internal data bus. Here's the ALU data bus for control. Okay, some CPU registers address control and how many bits are on these buses. How much memory can you hook up to a Z80? There's 16 bits of address. How many? It's byte addressable. Yeah, I know it's 2 to 16. Put that in human terms. Is it gigabyte? It's 64K. That's it. And it has registers. They use the Intel model. They letter them instead of number them, okay? But the accumulator is called A, and then after A came B. And then there's a C, but they make them, see, they pair these up here. And sometimes they're 8 bits each, and they try to make it look like 16 bits, and they do, that's Intel, see? They make it this like so complicated, actually. We just get you started with MIPS, which actually is ARM, which someone did a vlog and said that basically everything's ARM. Oh, here we go. So he wasn't using any interrupts and controls, and he wasn't using higher address bits. Pin number 30. See, this is messed up too. So actually the pins are going this way, so the upper address bits are on the end of the chip. So usually there's a dot. The dot tells you pin 1. And usually power and ground are in opposite corners. This is not the chip picture, okay? This is a functional. Let's see if we can see the chip picture. Well, let's go back to the web. Well, maybe an image. There you go. So he just got the saw and just cut right over here. See? It was Keith Kellogg. He was a brilliant guy. I wonder where he is these days.
You just ground the...
He wanted to fit physically in a package, and he didn't need the address bits, so he cut them off.
Yeah, but the ground was on that side.
Yeah, he hooked up the ground separate. There was actually multiple ground. All right, so we're trying an example, right? Zilog. So interface panel for an elevator is 8-bit application. Show the field encoding for memory addresses. All right, so how many bits on A? It has 16 bytes of main memory. Not very big, right? 4? Okay. Then two-way set associative map cache containing 4 lines. We have to figure out S, right? And a block size of 1 word. So in this case, if it's 8-bit words, 1 byte, so its number of bytes is going to be solving 2 to the 0 is 1 byte. W must be 0. Anything to 0 is 1. And we have 1 word per block, so another 0 for M. Now it turns out when M and W are 0, we don't write them. So in this case, we had a total of 4 lines, but it's two-way set associative, so there must be 2 lines per set. You have 4 total. A set contains 2 each, so therefore you have 2 sets. How many bits do you need to determine which is the set? It's either upper or lower. Is only 1 bit. Everything else left over is a tag. So here's how it works with the reference string. So you have 4 words of main memory, word size 1 byte, so you have 4 bytes of main memory. And you're referencing these byte addresses. I'm sorry, 4 bytes of cache. The main memory was 16, right? 4 bits, yeah, 16. 16 was it? Yeah. 16 bytes of main memory. So here's the main memory addresses. Now we're doing set associative, so if we had direct, it's going to be hit rate of 0 because of the ping pong. But But here, because it's set associative, some better things happen. So here's the 4 cache lines organized as 2 sets of 2 lines each. So we say K is 2. 2 ways means that the data can either go into this way or that way. There's 2 ways to keep it. That's where they got the word ways, okay? There's 2 ways. You can either be up here or down here. There's 2 ways you can store the data because it's fully associated within the set. So let's try the first access. So the way to solve these problems, always draw your field encoding first. Once you got the field encoding, you write this address in binary and put the bits here, and it tells you where to put the data. So here's 0 written in binary. So you have 1 bit of 0 is a set 0 or 1. So which is this an upper or lower? It's going to be an upper. And then what's left is a tag. You're going to say, well, I have 2 choices in upper. Where do I, which do I put? We're just going to fill in the order. It's arbitrary, actually. So the first reference is memory address 0. This is 0 written in binary. So the last bit is telling me it's the upper set. I have 2 choices, 2 ways to store it. I'll just pick the empty one on the top. The tag is the next 3 bits. What about address 4? What set number is it? Address 4 is in what set? Set 0 again. Look at the least significant bit. Is it a conflict miss though? No, because I have two ways to store things that go to that set. See, I can store it here. Now, if you have a 12 or an 8, then you're out of luck. Suppose you have a 10, you're out of luck. Anytime that you have a 0 in the least significant bit, which means it's an even number because it's binary, I showed you guys that trick, right? If it ends in 0, it's an even number. So anytime I have an even value come after this, I will have a conflict miss. But fortunately for this problem, we didn't have any more of those. But then guess what? We're going to reference 0. Did we find it? Yes or no? What we're going to do is look in which set? 0. And then what we're going to do is compare all these tags fully associative. Well, we have 2 to check to see if what? If you match, is 0, 0, 0 there? Yes, it's a hit. I should write this first because this is what we started with. And this is address 0. Yes, it's a hit. Why? Because we look in set 0, which is this upper row, upper 2 rows, upper half, and then we compare the tag. We have to match these 3 bits. It's bingo. Okay. So you're practicing for your old age. And then bingo. Match these things out. See, I got to start thinking ahead. What about next access? 4, same set, number 0, but now I got to match this tag as a match. You see, all these are hits. So if you keep going, do you have to solve the rest of these? No, you're not going to be hits. So we had 8 requests, 2 misses. What was the miss rate here? 6 out of 8. Under direct map, it was 8 out of 8 miss. When you say 8 out of 8, that's the miss rate, not the hit rate. Look what they ask you for. Someone's asking for the miss rate, give them the miss rate. So associativity helps with the ping pong effect. Is ping pong good or bad? Bad, yes. So we're going to reduce ping pong effect by getting rid of these conflict misses to some extent. If I saw an 8 here, or 12, or a 10, then you're going to start to have to get conflict misses, make some choices. Too many shoes, time to put some out in the, right? Or saying that when I'm working on the car, you have too many tools there, it's like you have too many sockets, right? You got to put some back in main memory, because the ones in the hubcap, right? The hubcap's full. So here's everything on one slide, okay? Don't be the guy that emails me and says, we have to memorize all these. You can say that, but just remember that these go to the next specific thing. This is the byte within the word. How many bits do I need? Well, if there's 2 bytes per word, I need 2 bits. What's the word? It's got to be given in the problem. How many words per what? Per line or block? Line and block's the same. And then what? The tags, whatever is left over. What's A? Is it address bus? You know this is the address bus. If you memorize it, it's hard. If you understand it, should not be too bad. Do you have to practice it? Absolutely, you have to practice it. Can you guys handle it? Yeah. Why? Because the next class they're going to think you think like this, because they're going to start talking about different caches and actually make it a lot even more complicated. In architecture, if you take architecture. So just take the time to understand it. I think it's easier. Here's a comparison table of what some of these values are for tag. It's always whatever is left over. Some of these definitions, memory capacity in bytes is 2 to the A number. We know what these are in Word. And then comparing, cache capacity is 2 to the N lines. Sometimes they give you units of lines. Sometimes they give you bytes. Sometimes they give you words. You guys can totally handle. Just be aware. Just be alert. So we've basically designed all the caches. Now we're going to talk about this replacement policies. Replacement policies follow what type of miss? We have compulsory, conflict, and capacity. So desktop is full, time to put some books back on the shelf, direct map caches. We never have to worry about replacement because it's automatic where we have to put it. So there's no decisions made like variability of what we're going to write over. Fully associative, you can see that there's some different strategies. I mentioned you can replace what's least recently used. That is leveraging temporal locality and says, well, if I haven't used it in a while, there's a good chance I moved on to a different part of the program. It's not like relevant anymore. That's least recently used. Or even though another thing is least frequently used, you can say counts the occurrence of reference without regards to the time. You know, there was like so many days in a row that I use this, even though I haven't used it for the last week, I'm just going to leave it there. Because I know it just is kind of like, it's kind of an aberration. Recently I haven't used it, but it's going to come up again because it's just so popular. This is about popularity. And this is about like, you know, what's on your mind in the recent past. So let's take an example. Here's an animation to get started. I think it's easy to see this animation. This is a computer science one. I didn't check before class if this is still live. Let's see. This is like a little whatever in Chrome. So here's our reference string. These are main memory addresses. How many lines in this cache? 3. Okay. So initially cache is empty, and then he's going to do is move this across and watch time go across the screen this way. So if it works, we can try. So you're at 7 is a compulsory miss. Next axis is 0. It's going to be compulsory miss. Now it's fully associative, so I can store it anywhere. My closet is a flexible mapping. I don't have to have shirts here, pants here, right? That's a set associative actually, right? You can have so many, you have a set of pants and you have a set of shirts and you have to put within the, inside is flexible. Here is completely flexible, it's fully associative. At this point, cache is full. At this point, if I reference any additional address that's not contained in cache, it's going to be a capacity miss. So here's 2. 2 was not in the cache. Cache's job is to say what I recently accessed to help us with temporal locality. So what is the policy here is least recently used. Of what was in the cache, 7, 0, and 1, which of those addresses was least recently used? 7. I look back in time. 1 was most recent, 0 was like next after that, and of the 3, 7 was the least recently used. It doesn't matter when it came in, when it was used. What about 0? 0 is a hit. What about 2? No, 3. 3 is a miss. What are we going to replace 3? Least recently used. I look back in time. 0 is most recently, then 2, and replace 1. I like that. Okay. You can watch the rest of the animation. We'll do an example. See, Pavlov's dogs. I just go to the next tab, see. So how do you build this in hardware? One way to build this in hardware is to use a counter as a register that increments up from every time we access this can be actually the clock input will be that when we get a hit. Remember we had hit line, we had a hit line. When that line goes to 1, we're going to increment that as a clock, saying that how many hits we've got. Now in this case, we have a counter that's referenced. Every cache line reference will increment the counter, and we're going to find out which of them is the least, okay? So we reset the counter, we increment it for the line. When a miss occurs, we replace the line with the one that the counter was 3, which was the longest in the past. So here's an example. This will be our last slide for today. Here's a reference string, just like we did in the video, but now I have 4. So what do? Initially cache is empty, so we put 5 and 6, 7 and 2 in order, right? These were hits, right? 5, 6 is a miss, 7 is a miss, but 5 is a hit, 6 is a hit, 7 is a hit, 2 is a miss. At this point, cache is full. Then what? Any misses from now, we got to replace, right? Because the closet is full. Yeah. I bought too many shoes. Then what? You buy another pair of shoes, so what? You got to put it in your closet. What do you got to kick out? Under this one, you're going to put the ones that you've least recently used. Not when you bought it. That we do actually, right? It's like I bought that shirt, I never used it, right? It's sad. Actually, you don't want to move it to the closet or to the garage, but that's 4. 4 is going to replace what? 5, because 5 was least recently used, because 2 is most, 7, 6. You guys are good with this, right? And what they ask you for the points is hit rate. Okay. But if you have your scrap paper, I'll give you partial credit. Okay, we're almost there. We've only got a few more slides in this module that we'll cover, and then we're into the last module of class. I am going to have class on Wednesday because they pay me. It's part of my job to be here, but we do have extra credit because we just keep that uniform at one point. But if you miss it, don't worry. Enjoy your Thanksgiving.
I don't know if you want to talk about it yet, but I was going to ask about for the final exam. Would you can you give us a number? Like, would you say 75% is new material, 25% old material?
I would love to, but I haven't made all of these.
Well, just do you know what in theory?
So I will. So I was looking at it. So I'll de-emphasize module 8 is device technology because that's kind of like a little bit on its own. Mm-hmm. But it's hard to decouple a lot of things. Like for sure I can say number 1 module, right? 1 was powers of 2 kind of bits and bytes, and then that's got to be there. And then module 2 abstractions kind of is going to be there in some form. And then 3 is MIPS. So the first few's got to be there, and performance will be there. But something like device technology, I can,
skip.
Yeah. But I don't know how to skimp on a lot of other parts. But I will give. What I'll do is, like you said, remind me getting closer to it, and then maybe when we come back, and then I can tell you guys more, so you can prepare. Cool. And then I've been thinking of it. I'll think over Thanksgiving, which is a good time because then everybody's happy, right? And then I'll think of a way for extra credit for that. And what I'm thinking is, if people want to come take it early, it's actually going to include also Monday there. But I know then everybody's going to want to take it Monday, but then the room overflows, right? Mm-hmm. So, but I'll give some extra credit for people that want to come maybe Wednesday. I can't give too much on Friday because other classes end on Friday, which would then it defeats the purpose if we're encouraging you to come and make more congestion, right? So, which then you're mad at me. So I will think about that. So there'll be some that, and we have a vlogger, I think next week, right? If I remember, I have to look at those vlogs. If you're a vlogger, send them me your YouTube's links. A few of them people did already. Thank you. And today we have extra credit today, right? Yeah. Okay. I did look at those earlier on the weekend. So everything in the extra credit we went over in class. So people that were here should be able to get a point today. And I'm still thinking about that pizza. We want to do pizza? I'm serious. Sure. So since I can actually buy for we can pitch in it. Everybody would just make a volunteer. Do you want it? So Domino's, they have this thing, right? You can see it getting baked, right? I don't know. My graduate student was showing me. It's like I don't know.
It's like,
I don't know, but he was showing me on his laptop. It's like, oh, yeah, it's on stage 2. Like he knows, like it's a pipeline. Like it's on stage 2 now. I'm in if we get the feta spinach feta one. I'm in. Seriously. But how long does it take? Right? It takes a half hour. But then someone has to get it, right?
They deliver.
So.
They bring it here?
Yeah.
So.
They deliver to the high school.
What we'll do is we'll do a few slides. I'll have to get my wallet, but then we'll be good, right? Unless somebody can spot. I'm good for the money, but if somebody can spot me, then I don't have to go upstairs. But if someone wants to put in your order, go for it. Okay. We're giving thanks, right? We're having a feast.
Are you really buying pizza for us?
What's that?
Are you really buying pizza for us?
I'm going to buy, I will buy a pizza, and I think there's enough people here if anybody wants to pitch in. We can, but how many people do we have here? Right? 1, 2.
We've got like 16, I'd guess.
So, I mean, we can't have 5 slices, but if we have 1 slice each, right, that's what, like, because right now they had a buy one, get one. They had a, so that's like, we probably need, what, like 3 or 4 pies, right?
I think 3.
3? But if we pay for 2, then we get 4, right? 4 is going to cover it.
Yeah, 4. I'll do it.
I think we came today, we should get something, right? Thanksgiving, see? All right, so let's see another strategy when the cache gets full. So we had 3 types of misses. What were anybody? What were the 3 types of misses? I'll start with C. 3 types of cache misses. They start with the letter C. Compulsory is when the cache is empty, and then we had conflict. Excellent. That's if the mapping strategy causes 2 blocks to map to the same line, even if there's space still available. And what was the last one? Capacity miss. Capacity miss is when you bought too many shoes. Okay, there's no place in the closet that's left. Okay. So when we have capacity miss, we have do replacement. Okay, so when we have direct map cache, no replacement. Why? Because it just has to go in one place. There's no choice. But when the cache becomes full with associative strategies, we have to make a choice. So now we're going to be given an associative cache. We just make it small if we can try it. We did last time least recently used. Let's look at least frequently used. Least frequently used, we have 4 lines. When capacity miss occurs, we're going to replace the line with the fewest references so far. So this is the way I think about it. LFU is a popularity contest. Which line is most popular? Okay, that's the one that we want to keep. We want to kick out or overwrite the one that's the least popular. It doesn't matter when. Okay, it's kind of like a historical, right? You know. For example, Babe Ruth, right, is in the past, but we always think of him we keep him as a prototypical baseball player, right? So that was a popularity thing. Same thing here, different than recency. Recency is temporal locality. This is number of references. So here's an example. Come on in. We're having a party. Literally, actually. Yeah. So address 5 is going to be loaded in because the cache is initially empty. Okay, so I'm just showing. I can show it's too many, right? So I just show. So initially it was empty. So then 5 gets loaded, 6 gets loaded, 7 gets loaded. You're going to say in what order? Actually, it doesn't matter because it's fully associative. The order is arbitrary. I'm just going to start filling it up. Okay. And then you hit 5, it's a hit, right? You hit on 6, you hit on 7 because they're there. And then 2 fills the cache. What does that mean? Any miss after that, you have to make a decision what to replace. Under this policy, we're going to use the least frequencies. Now, number 4 is reference. So we do have a miss. What do we replace? Which of these is least frequently used? Well, we use 5 twice, use 6 twice, use 7 twice, use 2 once. 2 it is. Okay, 2's gone, replaced with 4. And then 5 is a hit, 6 is a hit. So we have a hit ratio of 6 hits out of 11 total reference. And this is the least frequently used policy. What about Least recently used, how would this change? Would it change? And what would it be? Least recently, okay, so go back, right? Least recently used looks backwards in time from prediction of future accesses. This font size, maybe, I don't know. I just noticed it.